Well, comically enough, I was trying to import this graph that you're looking at right now in real time, and what I ended up doing was just turning the video off, which means we're going to have a part C, so now you should be in part C. So let's see here. Where did we leave off, right, before our... that I told you it was going to be an epic failure, and it was an epic failure. So where did we leave off? You took the limit as x approached infinity of 1 over 2 square roots of x times e to the x. You figured out that that's just 1 over infinity, which is 0. And now, the reason why I took a break from these analytical techniques is because it's good. If you want to get good at this stuff, right? If you want to get good at this stuff, you want to be able to take time and look at what the geometric interpretations are of some of these results. So the idea of limit as x approaches infinity. So what the heck does that mean, right? So here's the x-axis, and x is approaching infinity, right? X is growing. And when we say what is the limit as x approaches infinity of e to the negative x times the square root of x, we're really simply asking, what is our graph doing? Right? What is our graph approaching? What is y approaching as x approaches infinity? And what you're seeing is that, notice how your graph is approaching some horizontal asymptote, which is it's like an airplane that's about to land, right? But it's actually never does land, right? Because it's approaching. It just continues to get closer to 0 as x grows larger and larger. So do you see what we're talking about? So where does this answer 0 come from? Because that is exactly, look, if you kept drawing this green curve out farther and farther and farther, isn't it getting closer to 0? Right? Isn't the y value getting closer to 0? It is. That's what we mean, right? So I promise I won't take too many detours like that, right? I don't want too many parts in videos, but it is good. Again, if you want to get good at this stuff, it's good to take some breaks from these analytical techniques, start to look at some geometry along the way. Now, let's continue in our study. So we're asked to evaluate the limit, x is approaching infinity, of 1 plus 1 over x to the power of x. All right, now, if we try direct substitution, we basically get, so I'm going to erase this. If you were to try direct substitution right now, you would get, I'll tell you what, I'll use the color red because I'm going to, as if this is wrong. And you're getting, somebody has a red pen taking points off. Ready? So that way you know this is wrong. So if you tried direct substitution, well, 1 over infinity zeroes out. You end up with 1 to the power of infinity, which, again, intuitively, 1 to the power of 2 is 1, 1 to the power of 3 is 1, 1 to the power of 4 is 1. But using infinity like this creates problems, right? There's different usages and throughout mathematics of this concept of infinity, and the treatment of the infinity has consequences. Has consequences. So let's just agree that 1 to the infinity is an indeterminate form. It's not helpful for telling us about the limit. Okay, so if you will allow me that, then we can proceed to figure out what else we can do. Well, in this way, I'm going to I'm going to show you how, I'm going to rewrite this, right? This is one of those problems where we have to think about, we're going to think of it as an equation, as y equals the limit as x approaches infinity of 1 plus 1 over x to the power of x. All right, now I've rewritten the problem, and you should pause the video for a second, and you should consider what your options are. What could you do? Right? Because you remember, the goal is, can you get it into some type of indeterminate form where you can use L'Hopital's rule? So let's see if you and I are on the same page. So in my opinion, I'm looking at this x that's stuck in a variable here, and I'm thinking to myself, well, wait a minute, I have a way of dealing with that, right? If I take ln of, let's say, 2 to the power of x, I can rewrite that as x ln of 2, right? So okay, let me see if I can do something with that. But just know that you're not allowed just to take the natural log of the right side of the equation, right? Unless you're willing to compensate for that, right? Like this equal symbol is balancing. It's balancing both sides of this seesaw, if you will. And you're not allowed to just start adding weights or subtracting weights on one side unless you are willing to compensate by doing the same to the other side. So I am going to take ln of both sides of this equation. Only that I'm going to leave this limit out front of the ln, right? It's not required that I have this limit as x approaches infinity inside of an ln. I hope that doesn't confuse you. We will, in the end, we will evaluate the limit. The ln of what the ln is going to affect the variable. So what matters is that the expression 1 plus 1 over x to the power of x, what matters is that we are taking the ln of that. Okay, so now let me go ahead and use this log property that I set out to use. And when I do, that would give me, so I'll leave the left-hand side of the equation alone for right now. So that's ln of y. At no point in time did I evaluate the limit, so I'm still approaching infinity. And the only thing I'm going to do now is take this x and bring it out, right? Just like I took this x and brought it out. So now I have say x ln, and what's left? Well, what's left is still the 1 plus 1 over x. All right, well, now let's see what else we can do. So we're going to look just at the right-hand side of the equation right now. And we're still trying our best to set this up as a quotient so that I can use L'Hopital's rule. And let's see if you can follow me here. Okay, I'm going to leave the ln of y alone for right now. I'm going to leave the limit as x approaches infinity alone for right now. And what I'm going to do is I'm going to think about this as a fraction over 1. Ready? So I don't want to jump ahead. So I'm going to rewrite x ln of 1 plus 1 over x. Okay, I'll erase that. And I'm now going to simply divide it by 1. Right? And so that I can start thinking about how to form a quotient to apply this rule, this L'Hopital's rule. Well, what should I do here? What should I multiply by? So what I'm going to do, let's see if I'm going to write it, and then let's see if this makes sense to you. I'm going to go ahead and multiply by x to the negative 1 over x to the negative 1. Now, why? Why do I choose x to the negative 1? Well, because if you take a look at x times x to the negative 1, that's just 1, right? X over x is equal to 1. And then I can, in essence, I can then have a quotient of two different functions. Now, it should go without saying that x to the negative 1 divided by x to the negative 1 is equal to 1. So are you with me that all I did was multiply by 1? So, okay, so no, you're not going to, I don't think you'll argue much with me. Multiplying by 1 shouldn't change anything. So let me rewrite what we had. And now let me go ahead and rewrite what has changed. So now we're going to have 1 times x to the negative 1. So now I have x to the negative 1 in the denominator. And remember what I just said, that this x multiplied by this x to the negative 1 is just equal to 1. Right? That's just x over x. So now I'm just simply left with ln of 1 plus 1 over x in the numerator. And that's what I wanted, right? That was the goal of this process, was to be able to set up a quotient and of two different functions. And now I can start my L'Hopital's rule. Okay, so as of right now, I'm going to go ahead and take my derivatives. So we can think about this being f prime equals g prime equals, let me go ahead and write a time symbol. So let's go ahead and g prime equals. All right, so let me rewrite what this is going to look like. Okay, so now this line here basically says that all the work above this line was to get to the point in the problem where we are right now. If we had landed here, or if this was given to us in the beginning, then we could have jumped right in and started using L'Hopital's rule to evaluate the limit as x approaches infinity. Now, you may be wondering about this ln of y as well. And if you don't mind, let me go ahead and punt on that part right now. Okay. And I'll come back and I'll address where does the ln of y go, and so forth. Okay. So as of right now, let me go ahead and focus on taking the derivatives. So the limit as x approaches infinity, and let's rewrite this. So f prime, well, let's start there. So f prime so I'm taking the derivative, let's see here, so the derivative of ln of 1 plus 1 over x. Right, so this would be, if you don't mind, I'm gonna erase everything north of this horizontal line, just so I have some space. Okay. All right, so I want to take the derivative of that numerator, which is ln of 1 plus 1 over x. All right, well, this is, we can use substitution, if you recall. This is where you have u is equal to 1 plus 1 over x, which is just x to the negative 1. And then you need your u prime. And then you can set it up as such. So you can think of it as a chain rule. It's also, if you recall, probably depending on who you had, if you had me, the way I would have taught it is, if you have ln of u, it's just u prime over u, right? The derivative of ln of x is just 1 over x. But if you have more going on inside of your ln function, right? Like in this case, we have 1 plus 1 over x. It's just u prime over u. So in this case, we have u prime over u. Okay, so let me go ahead and rewrite that. So if I rewrite u prime over u, I'm going to get negative x to the negative 2 over u, which is 1 plus x to the negative 1. All right, so that's my f prime. Now my g prime is, well, if I'm taking the derivative of x to the negative 1, that's just going to end up being negative x to the negative 2. All right. Now, what I'm going to do is I'm going to take this whole piece and just all I'm going to do is flip some fractions and multiply. Hopefully some things will cancel. So let me go ahead and do that now. Let me come off to the side. So this is, let me grab this guy here. And let me go ahead and rework this. So let's simplify it. So I can think about that as negative 1 over x squared over, no, much easier. Anybody notice this? Sorry, but I do this in real time. Looking at the clock, looking at how much time I've spent on this problem, looks like it's taken longer than I wanted it to. So negative x to the negative 2 over 1 plus x to the negative 1. And now I'm going to basically flip and multiply. So that's 1 over negative x to the negative 2. And the good news is we have some things that cancel. All right. And what we're left with at that point is just 1 over 1 plus x to the negative 1. Okay? So that's what I'm going to drop down here. 1 over 1 plus x to the negative 1. Okay, so now can I actually evaluate my limit? I can. So if it helps you, you can think about that as 1 over 1 plus x to the negative 1 is just 1 over x. And now I can, if that helps you to think of it this way, now I can evaluate my limit. This becomes 1 over 1 plus, well, 1 divided by infinity is 0. So all of that work to get 1 over 1. And that is my answer. Okay? So that is, what is the limit as x approaches infinity? Well, it is indeed 1. Now, if you recall, and I think what I'm going to do, if you recall, we still had ln out here, right? First off, I want to stop. I want to pause and make sure that, well, I would love to say, are there any questions at this stage, right? Because more or less on L'Hopital's rule. I get it. I understand that we still have ln of y. Okay? So, but as of right now, more or less, I'm interested in, I would be interested if I had you in front of me to know that you understand the methods, the steps that we have undergone so that we could use L'Hopital's rule to evaluate the limit. At this stage, I just want to address where you would go from here. Right, so at this stage, you have ln of y is equal to 1. You would need to solve for y, right? So remember, e to the ln of e. This is the way that you would approach the problem. All right, so let's continue. So now we're asked about evaluating the limit as x approaches 0. Now, and this time it's to the right of 0, right? So let me get all my notes neat here. So now we're asked about evaluating the limit as x approaches 0 from the right side of sine of x to the power of x. Okay. So how do we do this here? Well, maybe it's worth, of course, you can always start with direct substitution, right? So if you tried substituting as it sits right now, again, I will use red, you would end up with 0 to the power of 0, right? That's if you use direct substitution. Sine of 0 to the power of 0, sine of 0 is 0. So that just gives us this indeterminate form of 0 to the power of 0. So, okay, so that's not going to work, so we have to roll up our sleeves. We have to figure out how to approach this. And one of the things that you should keep in mind is that if you have the variable x as an exponent, you're probably going to have to use that ln rule, right? That's probably the game that you're going to have to play. So let me go ahead and rewrite this guy such that I can take ln of both sides. Ready? So now I'm going to have y is equal to the limit as x approaches 0 from the right of sine of x to the power of x. Okay. So without too much of an aside, I'm going to go through the same procedure of taking ln of both sides. So now I'm going to have ln of y is equal to, let me go ahead and keep my limit on the outside of my ln. And now, so I'm taking ln of sine of x to the power of x. All right. And now the whole point of that was so that I can use that property that allows me to bring that log property that allows me to bring the x out in front of the ln. Ready? So let's go ahead and rewrite this. So I have the ln of y is equal to the limit as x approaches 0 from the right. And now what's changed is I have, instead of having ln of sine x to the power of x, I now have x ln sine of x. Okay, so if you were to try direct substitution right now, remember, in the beginning, if you tried direct substitution, it was 0 to the power of 0, right? And that it's not the form we want for L'Hopital's rule. Right now, if you were to try direct substitution, you would end up with you would end up with something like 0 times infinity, or actually, I think it'd be negative infinity, which is, again, an indeterminate form, but not the form that we want. We want 0 over 0 or infinity over infinity. So we need to think about how we can rewrite this. We want, remember, the game is you want a quotient. So, all right, let me rewrite everything that this ln of y equals the limit as x approaches 0 from the right. And now let's address how we're going to fix this. So in order to get this guy to a quotient, I'm going to have to multiply by something. Right, so let me rewrite. So this is going to be x ln sine of x. Let's see if you agree with me here. If I just simply multiply, I'll think about that as being over 1. And I'm just going to simply multiply by, well, you guessed it, it's going to be x to the negative 1 over x to the negative 1. Okay? So if I do that, I now have ln of y is equal to the limit as x approaches 0 from the right. The x times x to the negative 1 will divide itself out. That will leave me with ln sine of x over, and I'm going to write this as 1 over x. All right, well, what if I were to try evaluating the limit right now? Well, of course, it would still be at some indeterminate form. It would, if you evaluate the limit right now, it would be negative infinity over negative infinity. But that's because you haven't used L'Hopital's rule, right? At this stage, you want to finally take the derivative of f, take the derivative of g, and then we'll see where to go. Ready? So ln of y is equal to the limit as x approaches 0 from the right. And I'm going to go ahead and do some work here. So this is going to be f prime equals g prime equals, let's figure out what this looks like. So I end up with the derivative of, I got to go through this a little bit quicker. So the derivative of ln sine of x is going to give us cotangent of x, and the derivative of 1 over x is going to give us negative 1 over x squared. Okay, so let me go ahead and bring that down. So now I've taken the derivative, and it looks like this: cotangent of x over negative 1 over x squared. Okay, well, what's happening if we evaluate the limit, right? So if you plug in 0, well, we end up with 0 over 0 again. Right, so I mean, just all along the way, indeterminate. But the good news is that L'Hopital's rule allows you to apply it over and over again, until you finally get something that works. So let me see if I can continue this problem here. So at this stage, I want to go ahead and see if I can take the derivative again, right? Let's see if I can take the derivative again. All right, so I can rewrite this. I can rewrite this guy. So if I have cotangent over 1 over x squared, that can be rewritten. I'm running out of space. My apologies. When I start to run out of space, I start to scramble and think about how much can I fit in this tiny little area. And that's why I start to mumble, because I'm like, oh man, I'm running out of space. What am I going to do? But then I forget, wait a minute, I can just erase everything that's above and everything will be okay. All right, so let's see if this will be a little bit smoother now. I'm not worried about spacing issues. Okay, so I don't know. I'm trying to think about how to rewrite. I'm trying to think about how to approach this limit. Right now I'm still getting an indeterminate form of 0 over 0. I want to be able to take the derivative again. So, let's see here. What if we rewrite this? Let's see what happens if we do it this way. Ready? So cotangent of x over 1 multiplied by, I'm going to go ahead and, well, I'll tell you, I'll write it this way, divided by negative 1 over x squared. I'm going to flip and multiply. So that gives me negative x squared cotangent x. Right, so negative x squared cotangent x. Well, cotangent is the same thing as 1 over tangent. So that means that I can rewrite this as negative x squared times 1 tan of x, or negative x squared over tangent of x. Now, I'm thinking out loud as I solve this. So there may have been an easier way of doing this, but let me see what it looks like if I try this. Right? I have to be willing to look like an idiot. I have to be willing to take a gamble here. So now I can rewrite this as negative x squared over tan of x. All right, so again, if I evaluate the limit, it's still indeterminate. So let's go ahead and use L'Hopital's rule one more time. All right, so f prime, g prime. All right, so the derivative of negative x squared is negative 2x, and the derivative of tangent is secant squared. So let's rewrite everything. So I now have ln of y is equal to the limit x approaches 0 from the right. And now I have negative 2x over secant squared. All right, well, what happens if I evaluate the limit now? Well, negative 2 times 0 is 0. But actually, if you look at secant squared, right? If you look at secant squared, and you evaluate that the graph of secant squared, if you evaluate the limit as x approaches 0 from the right, it actually approaches 1. So this worked, right? I had to rearrange some things so that I could focus on graphs that I could, off the top of my head, which graphs could I picture in my head. But we do get 0 over 1, and of course 0 divided by 1 is just equal to 0. That leaves me with what? That leaves me with ln of y is equal to 0. All right, well, you would have to solve for y. But that is the gist. All right, I think we're going to call it quits. Hopefully you're able to stay with me. Hopefully you're able to stay with me through that problem. Sometimes it's hard if I don't have all my notes and I don't have your faces to keep me awake. I start daydreaming while I'm recording. So anyway, hopefully you were able to. There may have been a cleaner way of approaching that. I was just trying to use. I always think in terms of geometry, so I want to get to terms that I can picture the graphs in my head cleanly, and then I can think about limits as x approaches something. But nevertheless, it worked, and we are done, and I will see you soon.